Right now, you are moving. You are not walking. You are not driving. You are spinning at over 1,000 miles an hour, and you don't feel a thing. Your coffee doesn't spill. Your feet stay on the floor. But what if that stopped, just for 1 second? You'd assume the world would look the same the next moment. It wouldn't, not even close, because everything around you, the ocean, the air, your own body, is moving at that same rotational speed too. And speed doesn't like to disappear. It has to go somewhere. Here's the strange part. Physicists call this inertia, and it's really just a simple idea. Things in motion want to stay in motion unless something forces them to stop. Your body wants to keep spinning at over 1,000 miles an hour, even if the ground beneath you doesn't. So if the earth suddenly braked, you wouldn't stop with it. You would keep going, fast. Think about a car crash. The seatbelt catches your chest, but your head keeps moving. That's inertia in miniature. Now scale that up to planetary size and stretch it across every object on the surface at once. Buildings, trees, oceans, you. Even the air inside your lungs would behave this way. Every molecule of oxygen currently sitting in your chest is also spinning with the planet right now, at the exact same speed as everything else around you. That's part of why you never feel it. Nothing around you is standing still to compare yourself against. Speed only becomes noticeable through contrast, and right now, you have none. A 1-second stop doesn't sound violent. It sounds almost gentle, like a hiccup in time. But at the equator, the ground moves at roughly 1,670 kilometers per hour. Stop that in 1 second, and the deceleration is enormous. Anything not bolted directly into bedrock would be launched sideways at highway speeds or faster. Not thrown by an explosion, thrown by momentum that used to belong to the ground itself. And the ocean? The ocean doesn't care about your 1-second timeline. Water is fluid. It resists sudden changes even more stubbornly than solid ground does. If the crust stopped and the water kept moving, you'd get walls of ocean sliding across continents, not gently, but as a single, unstoppable surge. Geophysicists sometimes model this exact kind of energy transfer when studying megathrust earthquakes, moments when tectonic plates lock, then release enormous stored motion all at once. Which brings up something researchers already know happens, just on a much smaller scale. In 2011, the Tohoku earthquake in Japan was so massive that it actually changed how fast the Earth spins. NASA geophysicist Richard Gross calculated that the quake shifted the planet's mass distribution enough to shorten the length of a day by about 1.8 microseconds. Microseconds, not seconds. And that shift alone triggered tsunamis that reshaped coastlines. That single earthquake released an amount of energy scientists compared to hundreds of nuclear detonations, and it barely nudged the planet's spin. A full 1-second stop would require redirecting the momentum of the entire Earth at once, not just a section of tectonic plate. The scale isn't just bigger, it's almost impossible to translate into a number that means anything to a human mind trying to picture it. Now imagine that effect, not measured in microseconds, but flipped completely. A full stop. The energy involved isn't remotely comparable. It's not double or 1,000 times more. It's a difference in category entirely. But here's where the story gets strange in a different way. You wouldn't just feel it, you'd see it too, in ways your brain has never had to process before. The atmosphere is also spinning with the planet. If the ground stopped, the air above it wouldn't, at least not immediately. You'd experience wind, but calling it wind undersells it completely. This would be a horizontal blast moving at the same speed the ground used to be moving, over 1,000 miles an hour in most places, faster near the equator. For comparison, the strongest hurricanes on record barely exceed 300 kilometers per hour. This would be several times that, everywhere, all at once. Why does this matter to you, sitting here, reading this? Because your entire sense of stability, the feeling that the world is fixed and dependable, rests on something you never had to think about until this very moment. Stability isn't a guarantee, it's a byproduct of momentum staying consistent. For most of human history, that rotation was the only clock anyone had. Ancient civilizations built entire belief systems around the reliability of sunrise and sunset. Archaeologists studying sites like Stonehenge and the ancient Egyptian temple of Karnak have shown that early humans aligned massive stone structures specifically to track the sun's movement across the sky, a movement caused entirely by the planet's steady spin. That steadiness wasn't just useful, it became sacred. Cultures across the world independently built religions around the sun's dependable return, precisely because nothing else in early human life was nearly so predictable. Disease was random, weather was random, predators were random. The sunrise never was. So when you ask what would happen if the Earth stopped for 1 second, you're not just asking a physics question. You're poking at the single most reliable pattern early humans ever discovered. The one pattern so consistent it eventually became the foundation for religion, agriculture, and timekeeping itself. Farmers who miscalculated seasonal rotation risked starvation. Entire calendars, from the Mayan long count to ancient Chinese lunar solar systems, were elaborate human attempts to keep pace with a spin nobody could see and nobody could stop. There's a psychological layer here too. Cognitive scientists who study risk perception, including work associated with Daniel Kahneman's research on how humans judge unlikely events, have long shown that people are bad at fearing things that are physically enormous but statistically impossible, while overestimating dangers that are common but comparatively minor. A 1-second planetary stop falls into an odd category. It's not just unlikely. Under known physics, nothing plausible could cause the entire solid Earth to halt uniformly and instantly. Gravitational and rotational forces don't work that way. The planet doesn't have a brake pedal. So why does the question grip you anyway? Maybe because it forces you to notice something you've spent your entire life ignoring. You've never once consciously felt the Earth's rotation. Not today, not yesterday, not on your 10th birthday. Every second you've been alive, you've been carried along at incredible speed, and your senses were never built to register it. That's not an accident. Evolution shaped human perception around relative motion, not absolute motion. Your inner ear, your vestibular system, only detects acceleration and changes in speed, not steady, constant velocity. This is the same reason you don't feel the speed of a smoothly cruising airplane, only the turbulence. Constant motion, no matter how extreme, reads as stillness to a brain built for spotting sudden change. Which means the real twist isn't about the Earth stopping, it's about what your body has been doing this entire time without telling you. Consider the planet's actual spin more closely. It isn't perfectly steady either. Scientists have long known about something called the Chandler Wobble, a slight, irregular drift in the Earth's rotational axis, first documented by the American astronomer Seth Carlo Chandler in the 1890s. The planet doesn't spin like a flawless top. It wobbles, slightly, unpredictably, over multi-year cycles. And you've never felt that either. There's another layer to this most people never think about. The Earth's spin is also what gives you weight the way you experience it. Rotation creates a small outward force at the equator, which is part of why the planet bulges slightly there instead of forming a perfect sphere. Stop the spin, and that bulge has nowhere to go. Over time, without rotation pulling mass outward, gravity would begin reshaping the entire planet toward a more perfect sphere. Coastlines that have existed for thousands of years would slowly become obsolete. Not overnight, but the process would begin the instant that spin disappeared, if it ever could.
And there's the matter of day and night themselves. A stopped Earth wouldn't just be motionless. If it stayed stopped, it would eventually settle into showing one face permanently toward the sun, similar to how the moon always shows the same face toward Earth, a phenomenon called tidal locking. Half the planet would bake under endless daylight. The other half would freeze in permanent night. Astronomers who study exoplanets, including researchers investigating so-called tidally locked worlds orbiting red dwarf stars, have modeled exactly this kind of extreme climate split, and their simulations consistently show violent, permanent windstorms forming along the Terminator line, the narrow twilight band between the scorched side and the frozen side. It turns out a stopped Earth wouldn't just be strange for 1 second. It would become a fundamentally different kind of planet, forever. Why does any of this matter if it's physically impossible? Because it reveals something true about how fragile equilibrium actually is, even when it looks unshakable. The systems around you, weather, oceans, gravity, day and night, all rely on constant, uninterrupted motion to stay balanced. Remove the motion, even briefly, and balance doesn't just pause. It collapses into something entirely new. Consider your own skeleton for a moment. Bones and muscles are built to handle acceleration and deceleration within a narrow, survivable range. A car crash at even 30 miles an hour can be fatal without a seatbelt because the body decelerates far faster than tissue can absorb. Now compare that to a planetary stop, where the implied deceleration would be measured not in tens of miles an hour, but in over 1,000 within a single second. There is no seatbelt design, no survivable range, no biological mechanism that could carry a human body through that transition intact. This isn't a survivable disaster scenario. It's closer to a thought experiment in pure physics, useful precisely because it's so extreme that it clarifies the rules more ordinary events tend to hide. So here's the modern mirror. You move through life assuming stability is permanent, right up until something breaks it. A sudden job loss, an unexpected diagnosis, a relationship ending overnight. These moments feel like the ground stopping beneath you, and in a strange way, that metaphor is more literal than people usually realize. Your nervous system barely registers the slow, steady momentum of ordinary life. It only reacts to sudden change. Just like your inner ear ignoring a planet spinning at 1,000 miles an hour, your mind quietly ignores the slow accumulation of everyday risk, everyday effort, everyday motion, until something forces a halt. Ask yourself something. How much of your daily stability is real, and how much of it is simply motion you've never had to notice? The bills that get paid automatically, the habits that run without thought, the relationships that hold steady without daily maintenance. All of it moving, all of it invisible, right up until the day it isn't. Think about the last time something genuinely surprised you. Chances are, it wasn't a slow decline you could see coming. It was a sudden break in a pattern you had stopped paying attention to, precisely because it had been steady for so long. That's not a coincidence. That's the same mechanism at work, whether it's a planet or a person. Steadiness earns your trust, and trust earns your inattention. The two arrive together every time. There's a deeper irony buried in all of this. The very same rotation that would make a sudden stop so catastrophic is also the thing quietly protecting you every day. Earth's spin generates the Coriolis effect, the force that shapes hurricanes into spirals and steers ocean currents around the globe. Climate researchers who study atmospheric circulation, building on foundational work by 19th century physicist Gaspard Gustave de Coriolis, have shown that without this rotational influence, heat would distribute across the planet in a completely different pattern, likely making enormous regions far less habitable than they are now. In other words, the same spin that could destroy everything in an instant if it vanished is the same spin currently keeping the climate survivable in the first place. Danger and safety, in this case, come from the exact same source. There's a reason disaster scenarios like this one hook people so completely. They're not really about oceans or wind speeds or tectonic energy. They're rehearsals, a quiet way of asking your own brain what would happen if the invisible momentum holding your life together simply vanished for 1 second. Would you be thrown clear, or would you find something solid enough to hold on to? There's one last thing worth sitting with. Every measurement scientists use to describe time itself, seconds, minutes, days, was originally borrowed from the Earth's rotation. A second wasn't always defined by atomic vibrations in a cesium chamber, the way it is today under international standards. For most of history, a second was simply a fraction of one full spin. In a strange way, asking what happens if the Earth stops for 1 second is asking what happens if the very unit you're using to measure the event stops meaning anything at all. The question almost breaks its own math. The Earth isn't going to stop. Not in 1 second, not in your lifetime, not for a length of time meaningful to a human mind. The physics researchers agree on that much without much debate. But the question was never really about physics. It was about noticing, maybe for the first time, that you have been moving this entire time, carried by forces you cannot feel, trusting a momentum you never chose and never controlled. So tonight, when you lie down and the room feels perfectly still, remember this: it isn't still at all. You are hurtling through space, spinning with a planet that has never once asked your permission, and the only reason it feels calm is because nothing has forced it to stop yet.